In this video, you will learn to use Epsilon Near Field. Epsilon Near Field is a filter provided by Epsilon that allows you to visualize the aircraft body and especially to compute the near field forces acting upon the body. So basically, Epsilon Near Field is a filter that can be applied on the top of Epsilon aerodata. It generates basically two operations at the same time. The first action is to extract the surface body from the CFD domain. As a matter of fact, the domain contains a lot of information in BTK information, and it allows you to easily separate the BTK surface from the entire domain, from the volumetric cells. And once the body is separated from the domain, it simply computes the near field forces and moments acting upon the body. And this is printed here in the output messages. You have the near field forces decomposed into its pressure and friction components, and you have the X, Y, and Z components as a vector form, and you also have the moments. These components are referred always to the aerodynamic reference system, and that's the interest of having epsilon access to better interpret the signification of these components. Well, in order to understand how it works on the background, what operations are performed by Epsilon Near Field, we should have to understand that basically it takes information available at Epsilon aerodata. So what's the information that it takes? First of all, it takes the grid, basically. It will take the BTK and structured grid generated by Epsilon aerodata, because this is the data that will be used to extract the body surface. Also, it takes point data, especially static pressure and vorticity at the wall, because this will allow me to compute the near field forces, pressure and friction forces. And as well, it takes the field data, especially the reference surface, because this will allow me to reduce, to non-dimensionalize the near field forces. And it takes also the angle of attack, angle of side slip, and transformation matrix to perform some extra operations. So let's see how this information is manipulated inside Epsilon Near Field. The first operation that's performed inside the filter is to extract the body surface from the input data. And here you have several branches to follow depending on the type of the domain that you already inserted into Epsilon aerodata. Basically, there are four cases. The first case is the pure 2D case. For a pure 2D simulation, the first step is to extract the surface. Basically, let's say this is the 2D domain that we have been using in our previous tutorials, the NACA 12 airfoil. Basically, it extracts the surface. That is, we started from the structure domain. It generates just a surface, and this surface allows us to detect the edges of the boundary. Both these edges include the outer boundary, but also the body. So the main idea is basically to retain just the surface of the body and to ignore the external boundaries. And this is achieved by using a clip bicylinder operation. So basically you are generating a cylinder whose axis is normal to the CFD domain, to the CFD plane. And by defining this cylinder, you can clip the domain, take away the external boundary, and you will retain just the geometry of the body. So this is what you end up after this operation. You retain just the airfoil geometry for the case we are using in our tutorial. And after that, it generates an extrusion of these edges. Basically, it takes this geometry, these edges that are here, we generate an extrusion normal to the CFD domain, like shown here. And this generates an extruded surface that you can actually visualize on Epsilon Near Field. This will allow you to better visualize the surface parameters, like let's say the static pressure coefficient. And it also helps to compute the near field forces. We'll see that better afterwards. And again, all these are BTK operations that are performed on the background inside ParaView, inside the Epsilon Near Field. Now, that's all for the 2D case. Another possibility is what they call extruded 2D. Basically, this is the case, for example, if you use OpenFOAM or other CFD solver, it's typical to have a CFD domain, 2D CFD domains, with just one cell of thickness. Poses some problems because we cannot use this architecture. We have just to introduce some small modifications in our code to extract the body surface. Let me show you what it's done in the background. Basically, the operations are quite similar to the 2D case because the topology is relatively similar. The only thing that changes is this operation marked here in red, that is slice surface. What is this? Well, if I go back to the case of the 2D airfoil, let's say that we have a 2D airfoil with one cell of thickness for the case of OpenFOAM. Basically, this operation of a slice surface, it generates a slice just across the mid-span of this one cell thickness. And this allows me to extract the airfoil geometry. And afterwards, once I get the red line, I can generate the extraction and the same operations as before. So that's the only thing that changes on the background. You don't notice that when you use Epsilon Near Field, but it's very important to have those operations in mind when you execute the filter. And again, all of these are BTK operations. Well, the other case is the extruded 3D. This is typical of LES simulation when you're trying to simulate, for example, flow path in a cylinder with LES. In this case, you have multiple cells along the width of the airfoil, or the cylinder in this case. And then the way to extract the surface and to compute the near field forces is quite different compared to the previous two cases. So these are the operations that are actually made. The first of all is to extract surface. So basically, you start from the domain. This is a volumetric mesh, and you take away all the volumetric cells, and you retain just the external surface that includes the domain, but also includes the cylinder in this case. And then you perform a clip, two clips, first clip by cylinder and then a clip by box, that allows you to take away just the cylinder, and that's the geometry that you really want to retain, and that's actually the geometry that you will see at the output of the filter. Again, these are all BTK operations that are embedded in our Python code. You can actually modify that if you will. And the last case is the most common case for CFD analysis. That's the pure 3D geometries, pure 3D domain. This is just an example of a coarse case of UAV here. And the operations that we perform in the background are quite simple. First of all, we extract the surface. That is, we start from the volumetric domain. We ignore the volumetric cells and we retain just the shell that contains the CFD domain. That's basically the external surface. And again, this external surface includes the boundary conditions, the symmetry plane, but also the aircraft body. And that's what we really want to get. In order to separate the body from the rest of the surface, we use the clip by box. So this shows you better the idea. We start from the volumetric domain. We retain only the shell that contains the surface. And the idea is to retain just the aircraft body. And this is achieved with a clip by box. Basically, it generates a sort of box that will help you to clip and retain everything that is inside the box. So you have to define the starting and end X components, the starting and X, Y components of the cylinder, and the starting and end component of the vertical position of the box. So by defining these 6 positions, relative positions, you generate a box that clips out the geometry. That's all. That's the output of the filter. This allows you to take away the external surfaces, you retain just the aircraft body. And that's all. Well, once the body is extracted, in some cases you have to perform an extra operation known as a clean grid. What is that? Well, in some cases, especially if you're performing some multiprocessor simulation in the server, you start from single block CFD domain, but when you perform a multiprocessor, the solver splits the entire domain in multiple small domains to assign each domain to each processor. But the problem of doing that is that when you load the final convert simulation into ParaView, ParaView will recognize these interfaces separating each domain and will generate a sort of weird unphysical faces. These are actually surfaces inside ParaView. And we had to get rid of that, and I will show you how we achieve that. So let's start with this example. This is a 3D case, the LES case that I showed you for the flow pasta cylinder. If you extract surface, you will get rid of the internal volumetric cells, and you will theoretically retain just the external shell that contains the domain. But unfortunately, if you do just that, you will find out that there are internal surfaces. And these are internal surfaces, as I said before, correspond to the interface separating the domain that has been separated or split to assign to each processor. This is a problem because this will be considered as a surface and it will compute the near field forces on these interface surfaces. So we have to get rid of these internal surfaces. And this is achieved by using the clearing grid BTK operation. This is a close-up around the cylinder. You can see that you have actually the surface of the cylinder, the surface of the symmetry plane here, but you also have the surfaces separating each domain that has been separated for the multiprocessor solution. And this is what happens when you apply this BTK clearing grid operation. Basically, it takes away all those surfaces. It merges. There are duplicated points that are merged, and that makes it disappear, and you retain just the final surface that you will analyze. So once you have the body surface already extracted, you can actually go ahead and perform the near field operations. In order to do that, you have to first read data from the body surface. Basically, you have to convert the BTK arrays, that is the static pressure, vorticity, and so on that's available at the surface. These are BTK arrays inside ParaView. And you have to convert that into Python arrays in order to perform some extra operation inside the Python code. And again, you can still modify the code as you want. Once you have generated the Python variables with static pressure, vorticity, and so on, you can go ahead and compute the near field method. Basically, it computes the pressure and the friction forces acting at each cell of the surface. Please note that I'm talking about cell. Afterwards, in the practical session, I will show you that Epsilon aerodata generates point-based values. For example, the static pressure at the surface will be available as a point basis. But in order to compute the near field forces in an accurate manner, we have to perform these operations in a cell-based operation. So internally, Epsilon Near Field generates a transformation from point data to cell data. And this is for the sake of accuracy. Usually for surfaces like the cylinder that doesn't have some sharp edges, you don't notice the difference between the point-based approach and cell-based approach, but for most of aircraft applications where you have sharp trailing edges, you will really notice a difference, especially in drag. So by default, Epsilon computes near field forces in a cell-based, but you will always have the possibility to compute that in point-based if you want. So this shows you the normal acting at each cell. You can visualize that, and it's important to verify that the normals acting at each cell points in the right direction, that is pointing outwards the body. Otherwise, the near field forces that you compute will have the opposite sign. And once you have your cell-based parameters and the near field forces, you can actually integrate variables on the entire surface in order to get the actual drag, the actual lift. And again, this is performed by using BTK integration operations that are embedded inside the Python code. Once you integrate data, you just have to output that, send that to the output of ParaView, and this is just BTK poly data, and this is well suited for shell surfaces. So that's all. That all what's behind the Epsilon Near Field. All the steps that I showed you before, you will find out that all of them you can find and modify inside the interface of the filter. So let's go ahead and let's perform a live demonstration with the test case that you can find in the open data. Well, this is the case that we have studied in our previous tutorials. I have here the 2D case of the NACA 12 airfoil with an angle of attack of 10 degrees. I also have applied epsilon aerodata. So this is our starting point. On the top of here, I will apply epsilon near field. So first, make sure that you have click here and it's blue. So remind, if it's blue, it means that it is the active element on ParaView. So any operation that you applied, it will be applied on the top of this element. So I select this, it's now the element active, and now I can apply the Epsilon Near Field filter. Epsilon Near Field is this icon here. It's just an aircraft. That means that it extracts the surface from the CFD domain. So let's click here, and we'll generate this interface. The first element of the interface is the input type. Basically, you have to choose between 2D, 2D extruded, 3D extruded, and 3D. These are the 4 cases that I present you in the PowerPoint. Our case is 2D. We'll talk about the other elements afterwards. So let's retain 2D because that's our domain. And afterward, you have to define the reference chord. This is the data that's required to compute the pitching moment. So in our case, it's this value. And then you have to define the moment reference center to compute the moments. You can let it as it is or to place the quarter chord if you want, in our case, or 2D. But it's up to you to define the position that you want. Then clip radius is if you remember the PowerPoint, we define a cylinder normal to the domain that clips and takes away the airfoil, retain basically the airfoil and ignores the external edges of the boundary. So you have to define the radius. The cylinder that we use for the clip is centered at this position as well, at the moment reference center, and it uses this radius. So in my case, the airfoil have a chord of 0.4. So with a clip radius of 1, it will be fine. So let's click on apply. And as you can see, it has generated an extrusion. Just make sure that you change the visualization mode from 2D to 3D because this will allow you to interact with the body. If you click here on color, you will see all the parameters. The standard aerodynamic parameters are already generated in Epsilon aerodata, like static pressure. Except that this time you have an extrusion of the surface and you can better interpret this pressure distribution on the surface. That's better than seeing these values just along the edge of the airfoil in the 2D domain. But you also have some parameters like the near field forces, let's say the total force. This is a vector component. We'll show you the aerodynamic z-axis, that is lift. So this is the actual lift distribution on the airfoil that takes into account the pressure and friction forces. The physical interpretation of this will be tackled in separated videos. Now I was just trying to explain the interface. Let's stick to that. And you can change the extrusion length. By standard, it's just left 1 meter. It doesn't matter. It will not change the integration values. You can change, let's say, 2, and it will just longer. The length, You can choose that depending on your core and your CFD domain and so on. For my case, 1 meter of extrusion seems to be okay, but it's just a qualitative feature. Then here, once you execute the near field filter, you have some information that's printed here. First of all, it reminds you that you have selected 2D case. That's important. And it also reminds you to change the visualization mode from 3D to 2D. That is, this button here must be changed from 2D to 3D. Otherwise, you will not be able to turn the model like this. Then, and most important, it prints the near-field forces and near-field moments. As I mentioned during the presentation, it gives you the total and the pressure and friction component, as well as the components along the X, Y, and Z aerodynamic axis. That's very important and it's precise here. We're using the aerodynamic reference system for this component. You have deleted this information here. By the way, if you can delete the information printed here by clicking on clear if you want it. And let's say you have cleared that and you want to see the printed values, that is the lift and drag. Well, you can find out that information if you go to the field data. So in order to see that, go here, click on the plus button to generate a new layout. And then go here to the spreadsheet view. Be sure that you are showing Epsilon Near Field. It is the active element. By default, it is displayed here. And then you go to the attribute and select field data. And in field data, you have the values. You have the near field forces and friction, pressure, and total. And these are the X, Y, and Z components. It also reminds you the units. We have selected in Epsilon Aerodata the non-dimensionalization option. So these values are non-dimensionalized. This case, you have the lift coefficient of 1.1 and a drag coefficient of 154 drag count. And you also have, besides the moment, again, the components in friction, pressure, and total. And for each one, you have the X, Y, and Z components. And again, it reminds you that you are using non-dimensionalization. If you actually use the actual force unit, here will say newtons and then newton per meter here. Okay, I go back to my layout. Now I have to talk about these options here. You have flip normals, that's the first one. Let's say that lift that you find here, that's total force, that's the X, Y, and Z component. So the Z component is lift force. That's 1.1, it's positive, and it's okay because we have a 10 degrees angle of attack for an rifle and generates positive lift. Let's say it's negative. Well, if it's negative, that means that the surface normals are wrong, are pointing on the wrong direction. So you just have to click here and flip normals, and it will reverse the sign. You will see here that the near field forces total on the Z-axis, that is lift coefficient, this time is negative. But we'll let that by default. By default, it should work fine. It should provide you the proper value of the lift coefficient, like this is the case, 1.1, this is the lift coefficient. Then the other option is clean grid. This will allow you to clean the surface. Indeed, if you have that case of CFD data that had been run in the server with a multiprocessor computation, when you apply Epsilon Near Field by default as it is, you will see the extrusion of the airfoil edges, but also you will see all the weird internal surfaces also extruded. If that's the case, you just have to click here, relaunch, reapply the filter, and this will take some seconds, but it will clean up all these weird surfaces. Then you have the option of keep input data. You see that by default, the output of Epsilon Near Field just retain the Near Field parameters that we have computed inside the Python file, and also some specific data from Epsilon Aerodata. But let's say you want to visualize some extra parameter on the surface of the body. Well, you can do that. You can keep the data that's available at Epsilon data. For example, if you want to visualize the drag distribution by using arms, this change the values, let's say minus 0.1 plus 0.1. This is the field, the density field of the drag coefficient based on the arms exergy method. And let's say you want to visualize this parameter on the surface of the airfield. Well, you can do that. You can go to Epsilon Near Field, you activate here keep input data, and you reapply the filter. And this time, Epsilon Near Field, we have multiple parameters. Besides Near Field, of course, you have all the parameters that have been computed by Epsilon data. So you can go and choose your ART CD parameter, and you can visualize at the surface the part of the field that corresponds to the drag coefficient in this case. So this is quite useful for physics analysis. But just keep in mind that it will generate extra variables, a lot of extra variables, and that means that you will have an extra memory occupation. So if you don't really want to use it, just deselect that and reapply, so you have more memory. In some cases, you will struggle to generate the surface. That if you have some cases that are not foreseen in the usage of Epsilon, this is not common, and we have covered all the typical applications from aerodynamic analysis. But if you have some problems loading some specific complicated geometries, you can still have the option of load your own input data. But we will see that in another video. Then you have some options like set non-slip condition. Indeed, if you want to see, I go back to this option, keep input data, and I visualize the aerodynamic velocity component. The abs is the absolute velocity. You will see that the surface velocity is very small, but it is not exactly zero, as it should be. This is because the input data is cell-based. The ParaView ignores the information about the non-slip condition at the surface. It just has the information of the velocity at the nearest cell to the surface. And then we perform the conversion from cell data to point data. It will ignore the non-slip condition because it ignores it. This information is just available at the Fluent solver. So you can force that. You can force that the non-slip condition. It will improve that value. Of course, the apps will keep the same, but it will force that internally. So when apply this non-slip condition, you will not see a change because this value has been computed by Epsilon data. But internally, inside the Python code, this will be actually zero everywhere. You are forcing the non-slip condition. And this will improve slightly the drag prediction coefficient. Then this option by default allows you to integrate forces and moments. Of course, if you are using Epsilon Near Field, it's because you want to obtain the near field forces. But if you don't want it, if you just want to generate the surface and you don't want to compute extra parameters, you just click here and it will not compute the values. You can see this throw BTK empty array, so it just has extracted the surface, but no near field computation has been performed. And afterward, I go back here because I really want to compute lift and drag. You have the option to compute that in cell-based or point-based. As I mentioned in the presentation, it uses cell-based by default because this is more accurate. If you just keep in mind this value, total drag value of 217 drag counts, if I deselect that, it will perform point-based. And it changes the change is quite small. You see 217.6 when it's point-based, and now if I go back to cell-based, it's 217.7. So it's very small in this case, but in some cases, you might have some differences, one drag count. So it's always better to use cell-based as it is by default. Then you have some extra options like fourth wall vorticity. We will not talk about this because this is a development feature, but the option that you really want to use is the last one, save output in BTP format. This allows you to save what you're seeing on the screen. This is not epsilon data. This is the output of epsilon near field, that is the extruded surface in this case, will be saved as a BTP file in a specified path. So this is important because we are using this feature in multiple filters that we are used during the analysis. So please remember, if you need the extracted surface in other filters, or if you want to share your data with your colleagues, you can use this feature to generate a standalone BTP file that can be loaded into ParaView without the need of having Epsilon installed. So it's quite practical for exchanging results with your colleagues. So that's all for the 2D case. Now I will load the other cases to explain you the difference for the extruded and 3D and so on. Well, this is the other case. It's a 2D airfoil with a 1 cell thickness. This is not an open data that you may have in our website, but it's just a test case I will use to demonstrate the feature I mentioned before. I already executed Epsilon Aero data, and if you go to information, you will see that if you scroll down, you will see the bounds of the domain. As you can see, the Z mesh axis is normal to the plane. And if it's a perfectly 2D domain, the Z direction, the thickness in the Z direction will be 0. But if you take a look here, you will see there is a delta of 2 millimeters. That means there's a given thickness. And if you scroll down in the geometry, it's just an airfoil, you will see there's actually a 1 cell thickness. So this is the other case that I told you, and it must be treated differently inside the filter Epsilon Near Field, but for the end user it will be the same thing. If you go to Epsilon Aero data, you put it active, and then you click on Epsilon Near Field. The setup is quite similar, it's identical to the previous case. The only thing that will change is here. In input type, you have to change it to the extruded cell 1 cell. And normally, yes, you have the airfoil extruded, and the rest of the parameters is as you want. And as well, you have the near field forces, you have all the parameters here. So it's exactly the same for the final user, but it's good to have in mind how it behaves on the background. So in the case if you have some problems or you want to improve the code by yourself, you actually know how it works. This is the third case that I have prepared and corresponds to the 3D domain that has been extruded several cells along the width. This is not an open data that you will find in our website, but however, I will use this case to show you two separate features. The first thing that I want to show you corresponds to the internal surfaces that appear when you solve a solution with a multiprocessor. You can see that very easily with ParaView. If you see that the outside seems to be nothing special, you can see actually cylinder right inside. But if you put that in solid color and you change the opacity, you just scroll down here, opacity of the surface, you'll see that inside there are multiple weird surfaces corresponding to the separation of the domain into multiple domains to perform a solution with multiple colors. And if you extract surface, you will see that this is actually surface. And if you apply Epsilon Near Field on the top of that, you will find that out. Just click on Epsilon Near Field. Let's pick the third case. Let it all list by default, and let's see how it looks like. As you can see, when I apply the filter directly to the Epsilon Aero as it is, these weird surfaces are included. Even if I change the clip radius, it will just include more and more weird surfaces. So I have to get rid of that. Normally, you can use just this option here, clean grid, but it might not work for all the mesh types. There are some cases where this tool will not work. And in fact, this is a particular case like that. No, it works for most of the cases, but there are some cases that it doesn't. And this is that one. In fact, if you apply clean grid, it will show you nothing. So it's not working for that case. So if you had the bad luck to be in that case, there is a way to overcome that. Just go to Epsilon Aero data. And now we can see again the wear surfaces. And we just have to apply the filter manually. With this filter, BTK clean grid, we will apply that manually. So go to filters, alphabetical, and clean to grid. This will take some few seconds. And what it's doing is merging the duplicated points that exist at each point of the wear surfaces. And once these points are merged, the internal surfaces will disappear. And if, for example, I go here to clean to grid and I change the opacity, you will see that this time we don't have these wear surfaces because all the duplicated points have been merged out. If I activate Epsilon Add again, you will see the wear surfaces, but if I let choose clean to grid, we can see that it actually has disappeared. Now I have the geometry completely clean. I can apply Epsilon Near Field on the top of that. So I go to clean to grid, I apply Epsilon Near Field, and I change the type to 3D extruded, and I let it as a default, and this time I should get my cylinder. Yes. The clip radius is identical to the case. What changes this time is that you have the clip width. Clip width is the length of the output. That is, you have this domain with a certain width. You're taking with this parameter, you will retain a given percentage of the entire width. In this case, it's very, very close to 1. You can see that if I reduce it, let's say 0.8, the resulting geometry that you will retain will have a smaller width. But it should be always smaller than 1 because this will allow you to keep practically the entire surface without taking into account the lateral surfaces. If you put a larger number than 1, you will see that it will include the surfaces around, which you don't want to include, especially when you're trying to compute the near-field forces. So in order to avoid the appearance of those surfaces, you have to put a clip width smaller than 1. So typically by default should work and should retain practically the entire surface of the body. So that's all concerning this 3D extruded element, and then we will cover the last element of the options. This is the fourth and last case of type of data you can analyze with a Epsilon Near Field. And this is actually data you can download in our website and go to our website in Open Data, CFD Data. If you scroll down, you will find this case, the 3D subsonic case of a rectangular wing. You can download, execute Epsilon, and then you will be ready to apply Epsilon Near Field. Before applying Epsilon Near Field, I will show you what's the logic behind the extraction of the geometry. For those that who don't use ParaView very often, there is a way to extract the geometries by using this tool that's Clip. That's a native ParaView tool. Basically, what it does is take the input and just performs the clips to retain a part of the domain. There is a different clip types. In particular, we are using this one, box. And box basically it creates a box. It will retain everything what is inside the box. And what I want to do is that this box will be just around the geometry, the body itself, in order to retain just the geometry of the aircraft or the wing. And I want to then take away the rest, the boundary conditions and the symmetry plane. So the smarter way to achieve that is to use by using this option called reference bounds. Basically allows you to define the length of each one of the sides of this box in percentage of the total size of the domain. For example, you see in the x-axis this direction is established actually between 0 and 1, the total length. The initial position is 0, the final position is 1. So let's try to put this, let's say 0.4, you will see that it moves downstream, and the rear face I can make it advance by decreasing this value to 0.6, and now it's getting closer to the body is actually over there, and now I have to move this top face downwards and the bottom face upward. And that can be done if I modify again these parameters. Sorry, it wasn't this one, it was this. And this as well. I have to move that upwards. And now what I'm doing is I have a relatively good box here around the geometry. And I have to move this face to the left, so I have to keep modifying this. If I go inside, you will actually see the box well around the geometry. And if you apply, it will take just a few seconds. It will take the entire volume because you're applying this on Epsilon Aerodata. So what it happens inside Epsilon Near Field is that beside this clip operation, we're doing an extract surface. So let me do that by hand just to exemplify that. Go to Filters, Alphabeticals, Extract Surface. Extract Surface is here. So basically, I'm taking away all the volumetric cells. I will retain just the surface. And on the top of that, I will apply the clip. So now I'm applying the clip on extract surface, and now I got what I want. And as you can see, the clip operation now works fine and retains just the geometry. So this procedure of defining a box in percentage of the total bound limits is what is included inside Epsilon. I take the input data, I perform a surface extraction to eliminate all the volumetric cells, and then I perform a BTK clip operation by box defining the reference bounds. So all this happens inside Epsilon Near Field. So let me show you that. I go back to my case, this Epsilon Aerodata. It's a 3D volume with all the information executed. And on the top of that, I will apply Epsilon Near Field. And I will change the input type to 3D. And as you can see, I have here these three options, the X, Y, and Z minimum and maximum percentage are already predefined. As we said before, we use 04, 06 for the x-axis, 04, 06 for the z-axis, and the other phase was very close to 0 and 05. So it is predefined like this because if your CFD domain lies on the positive y-axis, it will work as it is by default. So if you apply by default, it will take away the geometry instantly. Just keep in mind that if you change that to 0, in some versions of ParaView might include the external surface, a part of the surface lying at the symmetry plane, which is undesirable. That's why by default I let a very small value, which is not 0 but it's very small. So this allows me to overcome this problem in some versions. In this one, that's 5.9.0, I don't have this problem. I can put really 0 and it will not get the symmetry surface. But that changes from one version to the other, so it's safe to put a very small value. The other options are identical to the 2D case. You have reference core, the reference center. The only thing that changes is this. So this covers all the 4 possibilities concerning the input data that must be processed by Epsilon Near Field. Now you're ready to keep analyzing your result. Basically, Epsilon Near Field, as we saw before, extracts the surface and gives you the near field values. Just a small thing before concluding this tutorial. If you are in Epsilon Aerodata in the options here, output variables, you haven't selected this one, Epsilon Near Field, what will happen is that when you execute Epsilon Near Field, you will extract the surface. That's no problem because Epsilon Aerodata will contain the geometry, so Epsilon Near Field will manage to extract the surface. But instead, it will not have the information of the static pressure, the vorticity, so it will not be able to compute the near field forces. So I will let you play with that. I will let you go here to Epsilon Aerodata. In the option of the output variables, you select analysis method. By default, it's all, so near field is included. So normally, if you let it as it is, it will work. But if you want to see what happened, so go to select and deselect Epsilon Near Field, then you execute Epsilon Data. This will take some minutes. And afterwards, if you go to Epsilon Near Field and you try to execute it, you will see that here in the vector values, you will see some weird elements. That means that the information required to compute these parameters is lacking, and that's simply because you forgot to activate Near Field in Epsilon Data. So keep in mind that the filters that you apply downstream of a given filter uses the information that this filter is providing. So keep in mind that when you perform an analysis, it's sometimes better to activate all the elements of Epsilon Aerodata in order to avoid this kind of problems of lack of information that's provided downstream. So that's all for Epsilon Near Field.